Hi everyone. So we have now introduced our power series, and in this topic we're gonna try to find solutions in our power series. And again, it will be second order and homogeneous. So we're gonna only look at homogeneous, although in principle we can also do the non-homogeneous, but let's not cover that. Homogeneous second order equations. And this can still be it's a large collection that could be studied, and there's a lot of things you can do, but we will concentrate on we narrow down to even much more manageable situations. So we're looking at something of the form, I'm using the notation of the book here, but again, this is just, don't pay too much attention to these symbols here. It's just a way of formulating this. So we assuming that these are polynomials actually. The pi are polynomials, and for us they will actually have a very low degree. In fact, this will be degree 2 at most, this degree 1, and this actually will be a constant in all that we will do. So it's homogeneous. It's not linear because it's not constant coefficients. If these will be constant polynomials, yes. If all degree 0, then we would have constant coefficients, and we know what to do. So the assumption is here that we're not in that case. And there is now two cases. So case 1 is, okay, so first, sorry, let me sorry, no, let me not say it this way. Let me say it this other way. So what we're looking for is a solution in power series, in a power series solution. So let me write that, a power series solution. But we know that there is one gimmick that power series have. They have a center. Okay, so so with center, and we know that the center as x0. This means that we will have a power series, so this will look something like this, right? Remember, you subtract the center. So this is how it looks, and the ans will be coefficients. And this is from 0 to infinity. Okay. So now there are two cases. So case 1 is that p of x0 is 0. So that this center that we're looking at makes this first term 0. Now, that doesn't mean that you can just ignore it, right? To the contrary, it makes it much harder. And this is the case that we call a singular point. So x0 is, we think of x0 as a point on the real axis, right? So that's why it's called point, or singular value if you want. And the case 2 is that x0 is not, so we're centering at, so x0 is the root. If x0 is not a root, then we call it an ordinary point. And so as you see, 7.2 is about ordinary points, and in fact even 7.3, so we'll do everything together here, so perhaps I should put 7.2 and 7.3. These are ordinary points, and that's what we're going to focus on first, okay, because singular points make life much harder. Now, there's a general fact now that there is a solution, so such a power series solution exists, so it exists, and we can even predict its radius of convergence. So with radius of convergence, at least it could be bigger. The distance from x0 to any root, to the nearest root of p0. Now, we're not going to pay too much attention to what I just wrote, but it is good to know this. So what I'm trying to say here is, so let's take an example here. Suppose we have this differential equation here. Is 0. It's a bit strange form, right? So there's an alpha there, and the alpha is not written in a very strange form, but that is a reason for it, that beyond the scope of this thing, but this has a name. This is called the Legendre equation with parameter alpha. This alpha, it depends only on alpha. All the other numbers, some fixed numbers. And Legendre again is a name of a person and a mathematician. And but rather than studying these things, seeing where this comes from, with this introduction to differential equations, I'm just going to look at this type of differential equation. So let's first talk about what are the singular points. So how do you find the singular points? Simple. These are the roots of this. P here. I meant P0 here. Sorry. That was a bit misleading that I didn't write a 0 here, right? So it is all about the polynomial in front of y double prime. Okay, these two don't matter. Okay, so for now we are looking at the zeros of this first polynomial here. So we're talking about the zeros of 1 minus x squared. So here P0 is 1 minus x squared. So it's better not to use this formula with P0 and P1s, and so just say it's the one that goes with y double prime. So the roots, so the singular points are the roots of this polynomial, which is of course easy. That is, this is x minus 1 times x plus 1, right? I up to negative sign, but it doesn't matter. So this is x is 1 and x is negative 1. So these will be the singular points. And studying, so in other words, if you would like a power series solution of the form x minus 1 to the n, this will be something that, because x is 1 is a singular point, these are techniques, this will be discussed in 7.4. We will talk a little bit about it, but not much. All this is just introduction, so we will say something, so C 7.4 for this type of things. So what really interesting are the ordinary points, and this of course are everything else. All x different from plus or minus 1. So for instance, x is 0. Okay. So what do I now mean here with this radius of convergence? So we know that there is going to be a solution centered at 0, so it will be something of this form, and it will converge. So the radius of convergence with radius of convergence r, and we know that r is going to be at least, well, the distance to the closest 0. So okay, here is our x0, which is 0, and here are the two roots, minus 1 and plus 1. So what is the distance here? Well, they're equidistant, so 1. So we will have a solution of radius of convergence at least 1. So for instance, take another one. If x is 3, say, so let's do this in a different color. So this is this is x0 is 0, this is x0 is 3. So now x0 would be here somewhere, right? Well, perhaps a little bit further even. So somewhere here, that's 3, this would be x0. And what is the distance now? Well, this is distance 2, this is distance 4. The smallest distance is 2. So we know that the radius of convergence will be at least 2. It could be bigger, but probably not. Very often it is not. Because the problem is exactly that what it means basically is that you're going to get these guys are always causing denominators. That you can there will be denominators that vanish at these points. For the solutions, we'll have denominators that vanish in these points, and of course you can then not plug in these points. So these the functions are not defined on these points. Okay. So the reason that the convergence is because you cannot plug in because of the denominators. I'm not want to explain the details. This is a topic on its own. This would be material for a graduate course. But now for us, this is just a distinction of the two things that we want to talk about. Okay, so how does it work? And let me do it on an example right away. The book has a lot of explanations and calculations, which I think are sometimes making life harder than necessary. So let's do an example. So I'm going to do much shorter than the book does, although the price is that sometimes you need to work a little bit more, but because the book throws all these formulas at you, and I don't want to do any formulas, just the method. And the method is straightforward. So, and I'm going to do it on an example. So let's do the example here. This is called a Chebyshev. Again, this is a mathematician. This equation is named after a mathematician, the Chebyshev's equation. So you see, many of these equations have names named after a mathematician. That tells you two things. Well, mathematicians were very interested in this thing, and these equations are so important that they acquire the name of their inventor, or perhaps not necessarily their inventor, or the person that studied them substantively. Okay, this is very typical for this field. You don't have this so much in other fields, but in differential equations you have all these names of equations because they all required a lot of thinking to how to solve them. And so what you be presented here are all these methods from centuries, at least 1 or 2 centuries, let's say 1 century and a half of mathematicians trying to solve these equations because they were important. That's why these equations had to do with physical phenomena. We have seen already examples of this. Now, okay, so all this for a long introduction to the equation itself. Here's the equation. Y double prime. No, sorry. No, here. Sorry, that's not the one I wanted to do. I'm sorry. Oh, I'm sorry. I said Chebyshev's equation. I'm not going to do that one. But my point is still there are all these equations named after things. So here is one. I'm just going to take one a little bit simpler to work with, to explain all the ideas here. So here is the guy that we will consider. And it's homogeneous. So you see it's second order. And you see here that I promised you these are going to polynomials and actually of rather low degree. This is degree 2, this is degree 1, this is constant. And this is throughout the examples, it will always be that simple. So let's see here. What are the singular points? Well, there is a 1 plus 2x squared equals 0. That means that x is 2x squared is equal to minus 1. So that means that x is plus or minus I radical 2. So they're complex numbers. Okay. Now, this is perhaps, in the previous example, I was discussing you about the radius of convergence, right? And I said it's the distance to the roots. Now here, what does it mean, the distance to the roots, if they're complex numbers? Well, okay, instead of working on the line, we are working now in the plane. What is this, where these points lie? Well, remember that this is the y-coordinate of a point. So this is the, so we would have radical 2 here and minus radical 2 here. So we are talking about these 2 points here in the plane. Now, I want to find a solution in, sorry, let me, which was the equation? Okay, I'm going to take it simple and I want a solution as a power series in X. And then we will do another example where we don't, but so it means the center here, x0 is 0. Okay, this is as simple as you can get. So where is that now? Well, 0 is this point, right? Is the origin. Remember now, so perhaps just a quick review what a complex plane looks like, right? So in general, if you have a complex number, a plus bi, then this we call the real part, this will be the imaginary part. So here is a, say, and here is, say, b. Then this is where the point is located. So this complex number is a point in the plane, and then we're talking about distance of points. So the point that we are interested in is the origin here, and so we see that the distance to the two roots, the two black points that I had, is radical 2. So we will know that this will have a solution, so we will know that the radius of convergence is going to be at least radical 2. But it most likely is just radical 2. Okay, so I don't want to say equal all the time because it might for some reason not be, but in general it will be just radical 2, which by the way is frustrating because this polynomial does not vanish on the reals. And so we know from a previous theorem that I didn't pay too much attention at either, that there exists a solution that there is a solution of this equation that is continuous everywhere, because the only obstacle is that this guy will somehow, the roots of this polynomial or the values that make this 0 are the only problematic points for to have a continuous solution. So there's a solution that is continuous everywhere, but we cannot find that solution in a power series. Our power series solution will only be up to radius radical 2. That's the sad story about this. This is how things work, and this is nothing we can do about that. Okay, but all this is not important. Here is now where it works. So we're looking for a solution power series in X. So we write the power series. It's basically the method of so it's the method of undetermined coefficients. But instead of writing just a polynomial of a certain degree, now we have to write the whole power series. So this is going to be y. And then we do what we always do. Well, we calculate y prime. But we have to do this formally. We don't really have to. So there is, I'll say that later, but the reason I'm not saying it now is because it's not going to make life easier. Although it's less formal, the calculations, you will have long lines and lines and lines of calculations. So it's really not so, it's better to write everything in this compact summation form. So what is the derivative? Well, that is n x n minus 1. We might have to shift or we might not have to shift. You'll see what happens. Y double prime, take one more time derivative, that's summation from n from 0 to infinity, n times n minus 1, a n, x to the n minus 2. Okay, and now we plug this in. So we would have, I'm going to be a little bit lazy here and put the coefficients here. So this will be 2 times that, this will be 6x times that, and this will be 1 plus 2x squared this. Okay. Now notice what happens here with the powers. Let me point it out here. This x, with this xn minus 1, is going to make it to xn. We know that if we want to add, we're going to have to add 2 times this, plus 6xy times this, plus 1 plus x squared y double prime this. We have to add them. We know we can only add if they have like terms. So we would have all powers of n here. But if I have this x multiply with this x minus 1, it will be a power of, it will be xn. I'll write it out. So let me get myself a little bit space here. In general, we're going to go a little bit faster, right? But so let me spell it out here. So what is the first one here? Okay, the first one is, of course, just, if I do 2 times this, sorry, it's not equal. I get summation 2an x to the n, and n from 0 to infinity. So let me keep writing that. What do I get here? Summation n going from 0 to infinity, 6n an, and now the x times xn is minus 1 becomes an xn. So there's no need to shift in here, and that's the reason why we look at this particular type of equation. However, this is unfortunately not fully the case in y double prime. Let's expand this here. So at one hand, if I just multiply with 1, and we will always try to make this 1. The cost is sometimes introducing fractions, so I'm not going to always do that, but ideally this would be a 1. Okay, then, because what we get then, okay, we just copy what we have, right? This is just the guy. Now notice that this is a power, the power here is n minus 2. We will have to shift here. But let's look at the second part. Plus 2, plus summation, no, I'm going to bring the 2 inside. So this is, I'm bringing the 2 inside. That means every of these coefficients. So we have here 2n, I don't have to write parentheses, 2n, n minus 1, an. And now what happens again is this square here, this x square times xn minus 2 will make it again x to the power n. So 3 of the 4 terms that we're going to have to add up are already in the right thing. So the only thing we need to do is just shift here. So we have to shift this. And perhaps I should keep track here of the bottoms. Although at some point I'm going to kind of not do this anymore, because for what you'll see what happens. Remember, how do we shift? We have to make this n minus 2 into an n. So we have to increase by 2. So we replace n by n plus 2. Let's do this. Summation n plus 2 equals 0. N becomes n plus 2. N minus 1 becomes n plus 2 minus 1. A index n becomes n plus 2. X to the n plus 2 minus 2 becomes n. And here we are. So, of course, let me make this simpler. This is just n plus 1, right? Now, what about this? What happens here on the bottom is, well, we should solve for n. So this means that n goes from negative 2 to infinity. But we said we will never take negative indices. And you might say, yeah, but can you just drop them just like that? What actually happens is, look at these indices here. What are we dropping? If I drop the first 2 of these, right? That's the first 2. So I want to replace this now. I'm saying, okay, this I'm just going to start from 0. You could say, but you're dropping 2 quantities. Is that allowed to? Yes, because look what the quantities are. The first quantity is when n is 0 in the original numbering, right? Well, that was 0. And n is 1, then this was also 0. So this looked like it started from 0, but it actually really only started from 2. And so then we would have n plus 2 equals 2, and we see n starts from 0. Okay? And because of this shift, in this case, the shift always works, so I don't need to worry about this anymore. So from now on, I'm no longer going to concern myself with the lower indices. And so I'm not going to write them anymore. Okay. Now, well, going back to what we were trying to do. So we have this one shifted one. Let me write this up. Summation. And I'm not going to write the indices anymore. n minus 1, a... Oh, I erased my... Oh, shoot. I erased the shifted version. Sorry. I need the shifted version. Where is he? Where are you shifted version? Ah, here you are. Okay, sorry. So what do I have now? So here I'm going back to adding these all up. So I'm doing this plus, plus, plus. And this has to be equal to 0, right? So let's write up. The shifted one was summation from 0 to infinity, but it's always the same, so I'm not going to bother with that anymore. n plus 1, 8n plus 2, and that is the power of x to the n, okay? This is x to the n, but I can combine them. They're all like terms, so I'm going to combine everything. So that, sorry, I need a bit more space. Let me rewrite this over here. Okay, sorry. Let me write it again. I'll write the index one more time, but as you'll see, I'll keep dropping it. So I'm going to write the coefficient of x to the n. Since I'm going to write it, I'm going to put it in the back because it's a long thing. It's easier to do it that way. From the shifted one, the green one, I get n plus 2 times n plus 1 times a n plus 2. Okay? I don't take the xn because I factored it out already. And now from the other ones, so I just take each of these guys here. Okay? Notice that they're all multiples of an. So here I can even factor more the an out. And what do we have then? 2n, n minus 1, plus 6n, plus 2. So these are, so if you want, this is this one, right? This one is this one, and then the triple one is this one, right? And I factored out the an already, so now I can close all my parentheses. And what we're saying is that this is equal to 0. Remember, because it's an homogeneous equation, what we did was, we said, okay, our solution looks like this, and now I'm going to take derivatives, the double derivative, plug this into equation, and we put it equal to 0. So this whole thing should be 0. Now what does that mean? That means that each of the coefficients have to be 0. Okay? So we get for all n's, we get that we have n plus 2 times n plus 1 an plus 2 plus an, and let's work out what is in the middle is. Expand this is 2n squared minus 2n plus 6n plus 2, and that has to be equal to 0. Okay? Notice there are two coefficients, the an plus 2 and the an. Okay? But we can simplify this, that is 2n squared plus 4n plus 2, and I can even factor out the 2 here, so it's n squared plus 2n plus 1. Oh, and I notice that this is a double product, so this is actually 2 times n plus 1 squared. Okay? So what do we do with such a thing? In general, we're never going to run into the general case, but I'm just saying what would in general happen is you would get various of these ANs. And you always take the biggest one, the one with the biggest index, and solve for that one. So I'm going to solve for this guy, the one that has the highest index. So solve for an plus 2. In our case, it's always going to be, because the particular form that we're looking at is going to be an plus 2. But if you ever take a second course in differential equations, you might have an an plus 3 and n plus 4 and so on, but you always take the biggest one. So solve for that one. So that means that we're going to bring, we get n plus 2 times n plus 1 an plus 2 is equal to minus this guy, minus 2 times n plus 1 square an, and then we divide both sides. So isolate this guy, it's minus 2 n plus 1 squared divided by n plus 2 times n plus 1. Oh, that something cancels, how nice. So this becomes minus 2 n plus 1 on the top and an n plus 2 on the bottom an. So you might say, but how is this a solution, Professor? Because I have now, can I solve this system of equations? Well, now comes the initial conditions, right? Because to find a solution, we always have to find the unique solution, we need an initial condition. So I'm going to take as initial condition here, let me take something. I'm just going to take something. Let me quickly look here. Let's take that that y of 0 is 2 and y prime of 0 y prime of 0, so give me a sec, is 3. Okay, let's just look at that. So how does this now work? Well, what we get is what we're getting here is called a recursion relation. This says that how an plus 2 depends on a value that is a smaller value. In general, there might be, as I said, there might be more ANs involved, but in this case, it is the an plus 2 is related to the an. So, for instance, what would a4 be? Let's try to figure out. Can we figure out what a4 is? Okay. So a4 would be, well, that means if I'm going to take a4, what is n then? 2, right? So this formula, I have to take 2 in. So I get, so here n is 2. In this formula, right? I'm talking about this formula, I'm taking n equals 2. So I should perhaps better indicate it that way. So I'm plugging in n is 2. Then on the left hand side I get a4, because 2 plus 2 is 4, right? And what I get on the other side? Well, minus 2 times 2 plus 1 is 3, divided by 4, a2. Right? A2. Professor, we don't know what A2 is. Well, let's do it again. What is A2? What should I do now using the same formula to get A2? Now n should be, therefore, let's do it in red. To get A2, I should take n equal to 0, right? If I plug in 0 there, on the left-hand side, I get A2. So let's plug in 0 on the right-hand side. I get minus 2 times 0 over 2 times A0. Okay, Professor, okay, so you're going backwards. Okay, you're doing something, but nothing is happening. But let's think about A0. What is A0? A0 is the starting coefficient. But if I plug in 0 in y, remember we have an initial condition. What is that? Well, all the powers of x cancel except for a0. So this is just a0. Ah, yeah, that's true, right? What is a1? Sorry, yes, what is a1? Well, let's look at the derivative here. Okay, what is the first non-zero term in here? Oh, n for n equals 0. No, I know. If n is 0, then it's actually 0. So the first non-zero term is for n equals 1. Then we get 1 times a1 to the power x to the power 1 minus 1. Nothing. So we have a1. And the next coefficient would be plus 2 times a2x, and so on. But what doesn't matter? All the other coefficients will have a power of x. The only power of x that is not really there, the 0th power, is when n is 1. And in that case, we have a1. So if I plug in 0, all these powers of x disappear except for the very first one, the first non-zero one, and that is a1. So this is just a1. So this is something that we always have, and let me write this here, that y0 will be just a0, sorry, yx0. X0 is the center, right? If you center the, so that will be where we take the initial conditions. That's the reason why we call these initial conditions. And y prime of x0 will be a1. That's always going to be the case. This is just the way we set up everything. Okay? So we know, in this particular, if we know a0, it was given to us. It was given to be, what did I say? y0, which is, y0 is 2. Is minus 2. So a2 is minus 2, so I can plug this in here. Then get minus 6/4 times minus 2. That is 12/4. That is actually 3. I found the value for a4. Okay, so what do I have now found? I remember, let me write here, a0, we know that it was 2, right? Okay. Well, a1 we also know. A1 is, that was given, right, and as what do I gave it to be 3, right? That's just now, we know now that this is just the second initial condition. So what is missing is a3, perhaps, a5, a6. Now let's think about it. Let's calculate a5. So what is a5? You say, why not a3 first? But you'll see. What is a5? Okay, so what should we do in our formula here? Let me box this formula. In this formula, what value of n should we take? N equals 3, right? So let me do this here in blue. So if I take n equals 3, then on the left-hand side I get a5. And on the right-hand side I get, well, plug in 3. That is minus 2 times 4 over 5 a3. But I told you, Professor, we need a3. Okay, yeah, okay. What is a3? Okay, so what should we plug in now? N is 1, right? So you see we're kind of plugging all the n's in 0, 1, 2, and 3 we have been plugging in now. So let's see what we get. So on the left-hand side we get 3 now. If we're plugging here n is 1. If we're plugging n equals 1 here, we get minus 2 times 2, that is minus 4. Well, let me write it up in parts so that you see where it comes from. So minus 2 times 2, and in the bottom I get, what was I plugging in? 3, a1. But I know a1. a1 is 3. So this is minus 4/3 times 3, so this is actually negative 4. But now that I know a3, I also know this guy. See, you're working yourself upwards now. Okay, what is this? Okay, so this is now minus 8 over 5 times negative 4. So this would be 32/5. Look, I have found, so I can write down the very first few terms. So y is 2, a0, plus 3 times a1, x, plus a2, x squared. What is a2? Minus 2. So minus 2x squared. a3, we calculated a3, was negative 4, so negative 4, and that would, a3 is the coefficient of x to the power 3. a4 will be the coefficient of x to the 4. What's the coefficient? Well, look, a4, that was calculated, that was 3, right? And then a5, 5, that was, where a5, that was 32/5. x to the fifth. At some point, you're going to have denominators. You see these things, where these things coming from, right? So this is how we solve this. And of course, there's a dot, dot, dot here. And the question is, can we now calculate each of these coefficients? Yes. If I want to know, for instance, A10, what should I do? Well, let's think about it. From A10, I would put n equals 8. So I would reduce the calculation of A10 to the calculation of A8. And then I have to do A8. That will reduce to A6. A6 to A4, and A4 we have already done by reducing it to A2, and then A2 to 0. So when we have an even index, by reducing each time 2 steps down, we will eventually get to this value, and we plug it in, and then we work our way back up. If we have an odd index, we do the same thing, but instead we will land at A1 at some point, and then we work our way back up. So if we go down and up, right? Down meaning you keep from here, A5, you calculate A3, and from A3 you calculate A5 in terms of A3, A3 in terms of A1, and once you have A1, you work yourself back up. That's what I mean here. So that is how this works. Now, the book spends a lot of time in showing that you can actually write down formulas of all that, but eventually, I'm not going to bother so much about that. I will be happy. I want you to be able to write down this general formula. These are called recursive things. But once we have these, I'm going to ask you to calculate up to certain the first five meaning A5. Technically the first 6, right? But up to power fifth. That's what we mean then. Okay, so and this is how it works in general. Then in the textbook they give all these neat little tricks you could do to shorten your calculation, but I'm thinking, well, I find figuring out the trick takes more time than actually the calculation of doing this. So I'm just going to do another example here. So here is the example, 2 plus 4x squared, no, sorry, plus 4x minus 2x squared, y prime, double prime, sorry, minus 12 x minus y prime minus 12y. Again, you see here the degrees are nice, right? But I want a power series solution in x minus 1. Okay. So, what should we do here? To make our calculations easier, we should write not only the power series, so this is what this means. We're looking for something, the center is 1, so we look at something of the form, of this form, right? Now, I want to have the same, remember here when we were doing this trickery here, we multiplied, we had this power, and they kind of magically made back our xn, and this square here made back this square, right? So we would like to write things, we wrote our polynomials in powers of x, what we always do, but now we're going to do a power series in powers of x minus 1. So we should also write our polynomials in that way. Okay? So how does that work? So how do you write? So how to write? I mean, the only one that is concerning us is the top one, right? How to write? And let me make. I'm going to make it a little bit simpler here, so we don't have to worry too much. Since I don't care. The textbook was trying to make a point, but I'm not trying to make this point, so I'm going to just write it this way. No, just minus 1 here. So no, just that, like that. Okay. I'll divide everything by 2 here. Oh no, that's not really yet what I wanted to do, but sorry, that's not what I want to do. I'm sorry. Let me no, okay, it's okay. I don't want to think much. So how to write 1 plus 2x minus x squared as a polynomial in x minus 1. Not in powers of x, but powers of x minus 1. Well, you write x as x minus 1 plus 1. You replace every x by x minus 1 plus 1. This is how you write x as a polynomial in x minus 1. Okay? As a polynomial in x minus 1, it has a constant term and a degree 1 term. And so now you replace this x, you replace x, every x here, by this expression. So let's do that. We get 1 plus 2 times x minus 1 plus 1 minus x minus 1 plus 1 squared. Now, you might be inclined to say, oh, let's simplify. No, I want to keep my parentheses x minus 1. I'm not allowed to open my parentheses in my calculation now. I'm keeping them closed up because I want to retain x minus 1. So let's work it out then. Okay, so the first one is not hard. We just distribute. It's 2 times x minus 1 plus 2. What happens here? Minus, well, double product formula. Remember, a plus b squared is a squared plus 2ab plus b squared, right? Okay, so let's do that. That's x minus 1 squared plus 2x minus 1 plus 1. Okay, so we have now everything in powers of 1. So let's see where are we at. We have 1 plus 2. So I'm looking at the constants here. 1 plus 2 plus 1, but with a negative 1. So there's a negative 1. So I get a 2. What are the coefficients of x minus 1? We have a 2 here and a minus 2. Actually, so that cancels. That's nice. And then finally, we have a minus. Minus. So there's a minus here. Minus x minus 1 squared. Okay, and this is a special form that makes the calculation nice. The fact that there's no x minus 1 term. This is why it's still nice. Okay, so let's rewrite it. So now we're going to rewrite our equation, rewriting this polynomial as a polynomial in x minus 1. So this will become now 2 minus x minus 1 squared y double prime minus 12 yeah, it's okay. I don't think it's much of an issue here. Minus 12 y prime no, sorry, 12 x minus 1 times y prime minus 12y is 0. Okay, so this is now the format we're going to look at, and so I'll put initial conditions later. Let me first work it out a little bit because, well, no, let's do this. Let's say y0 is going to be 4 and y prime 0, no, y1, sorry. Since I'm centered at 1 in powers of x minus the center, x minus 1, I have to give initial conditions here. Let's call this 6. And then this will be the A0 and this will be the A1 for exactly the same reasons as before. You can double check this, okay? So, okay, let's solve this now. Well, what we do is we propose a solution of this form. Let's write it up here. An x minus 1 to the power n. I'm not going to write the subscripts, the summations anymore. Okay, so what is y prime? Well, there's always the same, right? There's this, you can almost, and that y double prime is summation n minus 1 n x minus 1 to the power n minus 2. And now we have our coefficients. I'm going to write them. So this is minus 12 times that, minus 12 times x minus 1 times that, and then we have a 2 minus x minus 1 squared. Okay, so that's the multiplications we do. And again, so this is where we were doing all this for. This x minus 1 with this x minus 1 will make it x minus 1 to the n. So we will have to put it all to the same power, right? This one, multiplying this one will also do this. But of course, the only one that we won't have is this one. This will require a shift. So let me write it up one more time. So I'm going to do here this one first. So we get summation 2n, n minus 1, an, x minus 1, n minus 2. So this is the result of this one times that, right? Now the other ones are all going to be plus or minus, I guess. No, let me write the plus here. Summation. And so here this will be x minus 1 to the power n. Everything else is now already in the right power. I don't need to do the shift because of the way that I multiplied. So I repeat, because I have multiplied here with x minus 1 squared, this 2 n minus 2 plus 2 will make it n. So what we have is just this coefficient times minus 1. Don't forget there's a minus 1 there. So we get minus n minus 1 a n. Oh, and this is also all contains a n. So I can also factor out a n here. Sorry, yes. In this method you can do. Be careful. This is a special case. Later, I'll make a second video, is where we don't have such nice things happening, so we have to be a little bit more careful. But here, the powers are correct, and even the coefficient is always an. So again, what happens in the next one here? The x minus 1 and this x minus 1, n minus 1 makes it again the right power. There's an an here, so the coefficient, that's why I can factor this all out. And what is left is minus 12n. So, oops. Minus 12n, and then finally the top, well, that is just minus 12. Okay, and an is already factored out. So we can expand this as minus n squared plus n minus 12n minus 12. So this would be minus n squared minus 11n minus 12, whatever that is, it's not so important. Now we have to do the shift here. So let's do the shift. So we have to do n replaced by n plus 2. Again, the shift is always the same. So there will be n becomes n plus 2. N minus 1 becomes n plus 1, right? Then this becomes n plus 2. And then we have now, again, x minus 1 to the power n. And so what we have is, everything is now in powers of x minus 1 after this shift. So we have this plus this guy, right? Plus, let me write this one up. Plus, yeah, let me go a little bit lower here. So, plus, and then we had this summation, this coefficient, that is n squared plus 11n plus 12, I bring the minus sign out, an x minus 1 to the power n. And this has to be equal to 0 because it's a homogeneous equation. And so we see that what we get is 2n plus 2 n plus 1 an plus 2 minus n squared plus 11n plus 12 an is 0, and so we solve for that. So we bring that to the other side. 2n plus 2 n plus 1 an plus 2 is equal to n squared plus 11n plus 12 an, and then divided. So an plus 2 is equal to n squared plus 11n plus 12 over 2 times n plus 2 times n plus 1 an. Okay, I don't think anything cancels here, so let's not bother about this. And so this is again our recursive formula, the one that he had boxed in this case, in the previous one. So we have the same scenario. And so if we now have to calculate the various things, so let's calculate now A0, A1, A2, A3, A4, and A5. Let's go up to that, to 5. The first one, up to the power 5. Well, let's start with A5. How do we get A5? Well, we get A5 using this recursive equation here from 2 less A3, right? So this means I'm going to put in n equals 3 in here. So we do n equals 3. And that tells me that A5 is equal to 9 plus 33 plus 12 divided by 2 times 5 times 4, A3. Yeah, the number is getting a little bit ugly. I changed the numbers, and that's why it's not so nice anymore. But these numbers are never going to be really nice. Okay, there's going to be always fractions. So 9 plus 12 is 21. So this is 54, if I didn't make a mistake. 4, 6, 54. Yeah, 54 divided by 18. Oh, actually, does cancel a little bit, right? Yeah, so I can divide both sides by, oh, there's actually 3. Oh, okay. Oh, perhaps I chose the numbers better than the textbook. Okay, so A5. Oh, no, no, sorry. It's not equal to 3, right? What was the mistake I made? I forgot A3. There's an A3 here. So it is 3 times A3, but I don't know what A3 is. Okay, so what is A3? Well, you repeat the process, but now with n equals 1. And you get on the other side, you get 1 plus 11 plus 12 over 2 times 3 times 2. I replace n by 1 in each of these cases, and here of course I get A1. So that is 24 divided by 8, that is A1. There's an A1 there, don't forget, it's 3 times A1. And now we are done because we know that A1, remember, that was the initial condition, and I said this is the given just as the derivative at the center, so this was 6. So if A1 is 6, then I can calculate A3. So this means that A3, from this, I get now that A3, so now I'm going now the other way around, right? So I'm going from A1 is 6, I'm using the formula that I just have, that A3 is 3 times 6 is 18, and then I can find A5 by doing one more time, it's 3 times 18. So it's 3 times 18, which is, I guess, 54, right? 54. Okay. So I have A5, A3, and A1 already. What I'm missing is A4, A2, and A0. So let's start with A4. You see, you start from the biggest one because the other ones are going to come automatically. Okay, what do we do now? I hope by now it's getting more and more clear what we do, right? We replace n by 2, so we get 4 plus 22 plus 12 divided by 2 times 4 times 3, A2. Don't forget the A2. So that is 1638 over 1224, A2. I can simplify it. It's 19 over 12. This time it doesn't come out so nice. A2. 34, 38, right? Just make sure. If I make a mistake, then it's not really that much is gonna be happening, right? And then finally, how do we get A2? Because we still need A2. Well, we do this from putting in 0 in here. So n is 0. And that gives me A2 is equal to, if I plug in 0, then I have 12 over 2 times 1, A0. So that is 3 times A0, and A0 was, what was A0? A0 was 4. So A0 was 4. So plugging this in, I get that this is equal to 12. And plugging this in here, I get that this is equal to 19. Actually, my numbers were perfectly nice numbers that I chose, completely by accident. But so what does our series look like? Well, y equals A0, 4. A1 is 6. So 6 x to the power x? No, x minus 1. These are the coefficients of the powers of x minus 1. Plus A2 was 4. No, A2 was 12. Plus 12x minus 1 square. Plus A3, that was 18. Plus 18x minus 1 cube. What else? A4, that was 19. Plus 19x minus 1 to the 4th. Plus, and then A5 was 54 plus 54 times x minus 1 to the power 5. And then, of course, I should write dot, 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 because there are higher powers. And in principle, I can find as many as I want. Okay? The next question is, well, what about the radius of convergence? So just quickly addressing this. Well, what we need to look for is the roots here. What are the roots? These would give me the singular points. Okay, yeah, this tells me that 1 is not a singular point, because clearly if you plug in 1 you get 2, it's not 0. So we see that this, in order to solve here, x squared is equal to 2. So we see that x minus 1 is equal to radical 2, and therefore x is equal to plus or minus radical, so 1 plus minus radical 2. Okay, and we were plugging in 1, so we should make a little picture here. So we have, here is 1, we have 1 plus radical 2, 1 plus radical 2, and here is 1 minus radical 2. So again, we were actually right in the middle. That's just accident. That was just a choice. Don't make too much out of that yet. In general, in this particular case, yes. And so we see that the distance here is radical 2. So we know that the radius of convergence of this series will be at least radical 2. Okay? So we can plug in any number in this interval, basically, right? Because that is the radius. This is the integral. In other words, they're saying this is the radius. This is our, because of the symmetry here. This is our. We converge at least at those things. So, for instance, zero lies in here, right? The zero is somewhere here, right? Because radical 2 is bigger than 1. So, in other words, you can plug 0 in here, and you get the value of y. All right. So this is how these things work. Okay. So these were special cases where the calculations were neater, and I want to do this is in that was 7.2. 7.3 is the same but with a little bit uglier. Since their calculations get long and I don't want to make the videos too long, I'm going to make this in a separate video, but I'll keep that one shorter.